I would like to work through an example of the Hardy-Weinberg model so that you have a really good understanding of how to work through this. Now, when we're using the Hardy-Weinberg model, remember we have those 5 key assumptions that need to be made. When we look at those assumptions, it then begs the question, why would anybody use the Hardy-Weinberg model? Because those assumptions are very rarely ever seen in natural systems. And the whole reason why we're going to use the Hardy-Weinberg model is because it's very helpful for showing us whether or not we are potentially seeing evolution happening in a population, and specifically in relation to our lecture sites for being able to identify which type of natural selection we might be seeing within our population, whether that's directional selection, stabilizing selection, or in the case of the rock pocket mouse, disruptive or diversifying selection. So I want to follow through with the rock pocket mouse example. Remember, for our rock pocket mouse, we were looking at fur color. The dark color was dominant and that light color was recessive. So let's say we have a total population of 100 mice. Within that population, we count that 16 of those mice are light, meaning 16 of those mice are showing us a recessive phenotype. Now with the Hardy-Weinberg model, I know that I'm going to have those key variables that I have to define. So I know I'm going to have to define P, or the frequency of the dominant gene. I know I'm going to have to define Q. My equation is P plus Q equals 1, or 100% of the genes in the population. I know my other set of variables will be for the frequency of genotypes in the population. So this is where we have P squared, or the frequency of the homozygous dominant genotype, Q squared, the frequency of that homozygous recessive genotype, and then 2PQ, which is the frequency of the heterozygous genotype. My equation for determining the total amount, or making sure that I account for all the genotypes in the population, is P squared plus Q squared plus 2PQ equals 1, or 100% of my population. So I've been given the information, or I've seen or observed the information, that 16 out of 100 mice in my population have that light coloration. So I started with the Q squared, or homozygous recessive genotype variable, to define. The reason why is because I know that in order for a mouse to be showing me that light fur coloration, the only genotype that they can have is homozygous recessive, because the only genotype that shows recessive phenotype is a homozygous recessive genotype. So I start at Q squared. 16 divided by 100 gives me 0.16. This means that 16% of my population has that homozygous recessive genotype. I'm going to back calculate to figure out how frequently I'm going to see that recessive gene in my population, or how frequently it would be in my population. In order to do that, I'm going to take the square root of 0.16, which gives me 0.4. This means 40% of my population has that recessive gene. The reason why this can be more than what I'm physically seeing in my mice is because, remember, the heterozygous genotype. The heterozygous genotype has that recessive gene lurking in that genotype. So the possibility that I have individuals that are showing me black fur, showing me that dominant phenotype, yet have that recessive gene lurking in their heterozygous genotype, is a bit higher than what I'm actually physically seeing with the mice in my population. Now I can cheat here and use my equation. P plus Q equals 1. So if I figured out my Q variable, 1 minus 0.4 means that the frequency of that dominant gene, my P variable, is going to be 0.6. I take 0.6 times 0.6 in order to get my P squared. This gives me 0.36. I can use my equation. 0.36 plus 0.16 minus 1 will give me my 2PQ, or I can take 2 times 0.6 times 0.4. Either way, I'm going to get the same number, and that number is going to be 0.48. So 48% of my population is going to have that heterozygous genotype. 36% of my population is showing me the dominant phenotype with a homozygous dominant genotype, and just 16% of my population is showing me that recessive phenotype and has a homozygous recessive genotype. Hopefully this makes sense. Make sure that you can do these calculations without a calculator. If you have any questions, please email me.